Alright, for the following triangle, determine the indicated values, right? So we know this is a right angle triangle, so we can use our primary trig ratios. If we want to solve for x here, what we can do here is we have a reference angle, is 42 degrees. We have the hypotenuse, which is 5 centimeters, and this is where the primary trig ratios become really useful, is that we can understand that if you wanted to solve for x, using the reference angle 42 degrees, this is going to be our opposite side. This is going to be our hypotenuse, and this will always be our hypotenuse. This won't change, right? Because we can basically, because there's a right angle present, right? So the side length that's always across the right angle is always along the side. And we can solve for x by using the sine ratio because we have the opposite side and we have the hypotenuse. So you have 3 bits of information. If you know 2 out of the 3, you can solve for the missing link, right? I'm going to do sine 42 degrees is equal to the opposite side, x, over the hypotenuse, which is 5. In this case, x is equal to 5 times sine 42 degrees. And in this case, x is equal to 5 times sine 42 if we punch this out. And you can notice that you can actually find the value of the ratio if you plug it into your calculator. So make sure the settings of your calculator is in degrees, right? And we'll take a look at other measurements of angles later on. Right, so as long as your angle is in degrees, you can kind of solve for this, right? So in this case, sine 42 is equal to 0.6691. Okay, so I'm just going to use 4 decimal places for the time being. So it's 0.6691. If I multiply this by 5, we basically get 3.3457, and if I round this off, let's round it to 2 decimal places, it's 3.35 centimeters. Okay, so we actually solved for x, right? So it's 3.35 centimeters, right? Before solving for y, we can actually note that beta here, 42 degrees plus beta, should equal 90 degrees because these two are examples of complementary angles, right? So you could have actually started by doing that first. So beta here is 90 degrees minus 42 degrees, which is basically, should be 48 degrees, right? So this is 48 degrees. Okay, and put the degree sign and note that it is in degrees. It's important to keep the units on. And then what you can do here is you can solve for y really 3 different ways, right? You can use reference angle beta, you can use reference angle 42 degrees, or you can use Pythagorean Theorem. And we can actually note that you'll get the same value. So I'm going to just show you guys that. But remember that right angle triangles allow us to use Pythagorean Theorem. So we can understand that x squared plus y squared is equal to phi squared, right? Because a squared plus b squared should be equal to c squared according to Pythagorean Theorem. And in this case, we already solved for x. So 3.35 squared plus y squared, which we were trying to solve here, is equal to 5 squared. So y squared is equal to 5 squared minus 3.35 squared. And if I calculate this, right, I get 25 minus 3.35 squared. So that's going to give us 13.778. Okay, and y here, if I square root it, right, because you want to solve for y, not y squared, you get square root of 13.778. And in this case, what you're going to get here, 3.71 approximately. Okay, so I'm just going to keep all answers in 2 decimal places. So this is 3.71 centimeters, right? I'm going to show you that you're going to get the same answer by evaluating it using the trig ratios. Let's tell me to use beta just to kind of show you that you can do this multiple different ways. Right? So one of the beauties of math is that you don't have to do it a set way. You can approach problems in multiple different ways. Now if I use beta here, and we know beta is 48 degrees, I'm going to be using, because this becomes my reference angle, y becomes the opposite side, right? So I'm just going to use sine 48 degrees, right, which is beta, is equal to the opposite side, y, over the hypotenuse 5. Y is equal to 5 times sine 48 degrees, and y here is equal to 5 times sine 48, which is also 3.7157 centimeters. So it's approximately 3.72 centimeters, which is basically what we have here, right? So it's like 3.715. I could have had a rounding error here that's like caused a slight deviation, but you can notice here that it's the same value, right? So this just indicates that there's multiple different ways you can do this. We can also use the 42 degrees to solve for y by using cosine. Let's see that. I'm going to show you that it gives you the same value. Like if I do cosine 42 degrees, then it's adjacent side. So this becomes the adjacent side, right? Is adjacent side y over the hypotenuse 5, then y becomes, if I multiply 5 to both sides, you can solve for y, so 5 times cosine 42 degrees, and y is equal to 5 times cosine 42, which is approximately 3.7157 as well, right? So ideally, we would probably want to round this to 3.72 centimeters, but at the end of the day, it's the same thing, right? So this can show you guys that you can do, you can approach trig questions when you're solving for a missing side multiple different ways, and if the case does present itself, you can also employ Pythagorean Theorem. So all of these things are related. So that's what the power of trig really is. All right, let's solve for the following triangle by finding all missing sides and angles. Now, in this case, we're not given any angles. We know this is a right angle triangle, so we can utilize our primary trig ratios, but we are given two sides, right? Now, you can actually solve for side length x by using Pythagorean Theorem, right? So I'm going to just do that out really quickly, but I also want to demonstrate that you can do this by using trig. Now, if we do use Pythagorean Theorem, we can understand that c squared, which is the hypotenuse is always located across from this angle, from the right angle. C squared, the hypotenuse, minus b squared, which is any of the other two sides, is equal to a squared, right? So in this case, a squared is x, right? So you can understand that 7.2 squared minus 4.1 squared is equal to x squared. So therefore, x is equal to the square root of 7.2 squared minus 4.1 squared. Okay, so in this case, we can see that if I crunch this out in my calculator, it's 7.2 squared minus 4.1 squared, and this is going to give us 5.9186 centimeters. Okay, I'm going to keep it into 4 decimal places because I want to see how accurate my trigonometric procedure in calculating this missing side will be to this Pythagorean theorem. Okay, so we calculated that x is 5.9186 centimeters. Now, the big question here is how do we find these angles, right? Now, to find the angles, I'm going to use, for alpha, let's use rad here. Okay, so this is angle alpha. To find alpha here, right, we can notice that this becomes the opposite side. So x is the opposite side, right? Let's say we label this side length A. Let's call this guy C, and let's call this guy B, right? So this is side length C, this is side length B, and this is side length A, right? And it's just another way of looking at it. And so this is your opposite side here, and this will always, C will always be a hypotenuse, so this is going to become the adjacent side. B is our adjacent side, right? And we can understand here that if we didn't solve for x, we do have the value of our adjacent side over hypotenuse. So cosine of alpha is equal to 4.1 over 7.2. Okay, let's assume that I didn't solve for x here. Okay, I'm going to just look at the information that I've given, and if you figure out what this value of this ratio is, 4.1 divided by 7.2 is going to give us 0.5694. Okay, so we get 0.5694. Now, in order to solve for alpha, I need to get rid of this cosine, and we do something called an inverse. It's called a cosine inverse. We do the cosine inverse of cosine alpha, and this actually cancels out the cosine. So each function has its own inverse, right? So if you have sine theta, right? If you do the sine inverse of sine theta, then you basically get theta. If you do cosine inverse of cosine theta, you basically get theta because the cosine and the cosine inverse cancel out. And if you do the tan inverse of tan theta, you basically also get theta. So the inverses just cancel out the ratio, like the value of the ratio. And in this case, we can see here that cosine inverse of cosine alpha, it will give us alpha. But whatever you do to one side of the equation, in order to keep it the same, you have to do it to the other side. So cosine inverse of 0.5694. So now you can see that alpha is equal to the cosine inverse of 0.5694. And if I punch this in my calculator, you should see that alpha is equal to 55.29 degrees. I'm going to round to the nearest degree, so let's do 55 degrees. So if alpha is 55 degrees, you can then solve for beta, because we can understand that beta is complementary to alpha, right? Alpha and beta are complementary angles. And in this case, beta should be equal to 90 degrees minus alpha, which is 55 degrees, which should also be 90 minus 55 is 35 degrees. Now let's say that we want to solve it a different way. Well, using beta here as my reference angle, then this becomes the opposite side, right? This will become the adjacent side, and then the hypotenuse will still remain at 7.2. So in that sense, we can understand the sine of beta using our previous values will give us 4.1 over 7.2, right? We found the ratio of this, so sine of beta is equal to 0.5694, so, right? We calculated the ratio of this. So beta here, if you want to solve for beta, what you need to do here is you need to do the sine inverse of both sides. So sine inverse of sine beta is equal to the sine inverse of 0.5694, and then the sine inverse and the sine cancel out, so we get beta is equal to the sine inverse of 0.5694. So if I do that in my calculator, you actually get a different value. You actually get the same value. You get like 34.708 degrees. If I round that to the nearest degree, it's about 35 degrees. So you can actually see that you get the same value. Okay, this is really useful, and it does really help us to kind of understand this, right? So you can actually see that beta will give us the same value. Now, in that sense, right, so we know how to solve for alpha and beta, right? So alpha here is 55 degrees, so rounding into the nearest angle, and beta here is, let's say, beta here is 35 degrees if I round to the nearest angle. And I want to solve for x. Well, you can use any of these two angles now, right? Let's just use alpha, and you'll see that you'll get the same answer. So let's say we're using alpha. So alpha, this will become the opposite side, so we can understand the sine of alpha, which is basically 55 degrees, is equal to basically x, the opposite side, of the hypotenuse, 7.2. If I want to solve for x, I'm going to multiply 7.2 to both sides, cancels out. X is equal to 7.2, times sine 55 degrees. And in this case, x is going to be equal to, so 7.2 times sine 55 degrees is going to be equal to about 5.8978, right? You can notice that it's very close. Like this is going to be 5.9, this is going to be 5.9, right? And one of the reasons because is I rounded the angle off, right? So if you do keep it as accurate as possible, right? I had 55.29, right? So if I did 77.2 times sine 55.29, you can see that you'll get 5.9187. So it's very close. It's exactly the same, right? Like if I do sine 55.29 in my calculator, you can actually note that you would get 5.9187, right? So if you actually use the original value, you can see that the margin of error between Pythagorean Theorem and utilizing trig here, right? The trig value and using Pythagorean Theorem, using the trig ratios in Pythagorean Theorem, these are very close, right? So now we've solved for x, and we can say that x is equal to, let's say, 5.92, right? And that's basically our triangle in a nutshell. We've solved for a triangle. So you can use a combination of these trig ratios, the inverse of the ratios, Pythagorean theorem to basically solve out a right angle triangle. So it's really useful to understand.